As we said, the topic today, jumping ahead, is going to be inverse Z transforms. We want to get to that to really finish off the last analytical technique we need to be able to use Z transforms effectively. What we're addressing today are the kind of applications that require inverse transforms. And typically that's going to be either when we're finding unit sample responses. We've seen that we can do that with discrete time Fourier transforms, but it's probably actually more easily done with Z transforms. We know we can find the unit sample response of the system by solving the linear constant coefficient difference equation for a special set of initial conditions. Or, and this is probably usually the better way to do it, we can transform the difference equation using Z transforms, rearrange y of z over x of z to get the transfer function h of z, and then just inverse Z transform h of z to get h of n, the unit sample response. Typically, that's going to be the preferred way to do this. The other kind of system analysis that usually requires this is doing zero state responses or ultimately doing total responses. Today we'll have enough information that we can go ahead and, just as we could do with the DTFT, we can find the zero state response of a relaxed system for a given input that we can transform. And we'll do that by effectively doing convolution, but doing it in the transform domain, in this case the Z transform domain, just like we could do it with the discrete time Fourier transform, because in the transform domain that convolution becomes simply multiplication. And so we can take our transfer function that we can easily find from the difference equation, multiply it by the Z transform of the input. That gives us the Z transform of the output. But then we need to do an inverse Z transform to get back to the time domain where the answer lies that we really want. So today we're going to go through what are all the different methods we have for performing the inverse Z transform. And as with most of our transforms, we have a number of options, including, of course, if all else fails, we can always fall back to using the inverse transform definition, the equation for that. Barring that, then the typical way we're going to want to do it is simply by table lookup. If we have a simple form of Z transform, we can look it up in a Z transform table and find its inverse transform directly. Or if we have a little more complicated one, but still fairly simple, maybe one that doesn't exactly resemble one of the transform pairs in the Z transform table, but a modified version of it, then if we understand the properties of the Z transform, how it operates when we do time shifts, time expansions, scaling, shifting, things like that, then we can recognize when those different operations are applied to our signals and to our transforms, and use the combination of our properties table and the transform table to get us through the inverse transform. Barring that, if we have a more complicated expression, which is more typically the case, usually if we have something with higher than a second order denominator in the thing that we're trying to inverse transform, we've got to revert to doing either long division if we just want sample values, or partial fraction expansion if we want to get an analytical closed form solution. And when we do partial fraction expansions, we're trying to break up the more complicated function, be it a transfer function h of z or an output signal Z transform y of z, and turn it into a collection of forms that match entries in the partial fraction expansion transform table, so we can simply look up again what the inverse transform will be. Just illustrate a couple of these different techniques, let's start with an example here where our transfer function h of z is a 5z divided by z minus 0.1 quantity squared, and we want to know what is the unit sample response for this system. For that, we simply need to inverse transform our h of z. Now, we could start off by using the defining definition equation for the inverse Z transform, which if h of z is the Z transform and we want the inverse transform h of n, it's 1 over 2 pi j times the integral over closed contour of the complex function h of z, z to the n minus 1 dz. Now, that's a strange looking integral sign because that's not your typical kind of integral. H of z is a complex function, so this is a complex integral, and we see that reinforced by this 2j we have in the denominator of inverse transform. And that happens to be a closed contour integral on a complex plane, which is something that you likely haven't learned how to solve yet. That's usually something reserved when you get to the graduate and master's level. And so we really don't have at our disposal the ability to use this definition for our inverse transform. It is a complex contour integral that requires finding residues for the inverse, for the completing that integration. And so, no, we're not going to even try to use the equation for the inverse transform in this case. But what we are going to end up doing in terms of partial fraction expansion is, in fact, the way that we attack these kind of problems, is how we find the residues of the poles of such complex functions. So instead of pulling out the definition, we could use the lookup tables if we have a simple enough case, and we do this time. We have a second order denominator. And so we're looking for, in the Z-transform table on the right side, on the transform side, a function that matches, or at least a form that matches one of these examples, and that matches with its region of convergence as well, so that we can simply move over and observe what the inverse transform is from the table. In our case, 5z over z minus 0.1 squared, we see there is an entry that looks just like that. The denominator matches as long as we assign the value of 0.1 to alpha. Now we notice alpha has to appear in the numerator, so I need to manipulate my h of z so that it has that 0.1 in the denominator term and also in the numerator. So we need a multiplier out in front so that together we get back to our original value in the numerator. With that said, then we can simply look up that the inverse transform of this z to the z times alpha over z minus alpha squared is n alpha to the n u of n. Alpha is 0.1, so we have an n times 0.1 to the n u of n, and our multiplier 50 out in front comes right across. Now, in the inverse transform, we have the same issue that we had in the inverse. The inverse transform, we have the same issue we had in the forward transform, which is namely that there are actually two different functions that have the same z transform, one that's causal, one that's anti-causal. And so it's not sufficient to just look up the table and assume that everything is going to be one or the other. We usually need to have one other piece of information to confirm for us which is the correct inverse transform to use. It's always the case that there's two different transforms that are two different time functions that have the same transform. The only thing that's going to differ on them is the region of convergence of the two. The causal version and the anti-causal version will have opposite regions of convergence. Causal one will have a region of convergence starting somewhere and going outward. The anti-causal version will have a region of convergence that begins at some radius and goes inward. So you need to tell me either what is the region of convergence, tell me explicitly that it's causal or anti-causal, or tell me if it's stable or unstable, and I can infer which it must be based on the pole positions. So in our case, there was actually two different options for the inverse transform of our original h of z, the causal version and the anti-causal version. Now, if you tell me that it's causal, then obviously we know it's the u of n1. If you tell me it's stable, then I have to look at where the poles are. In this case, I have poles, two poles at z equals plus 1/10. That's inside the unit circle. And if my region of convergence begins at the outermost pole and goes outward, which it would for a causal system, then it can include the unit circle, which is the criterion I need for a stable system. So it only makes sense that if the system is stable, it has to be the causal case. Because if it was the anti-causal case, having these poles inside the unit circle would require the region of convergence to start inside of be less than 0.1 and go inward. It would not include the unit circle, so it couldn't be stable. So with stability, we need to evaluate where the poles are in relationship to it to tell whether it's anti-causal or causal. So for us, tell me it's causal, tell me it's stable, or tell me what its region of convergence is. That helps me to determine that, yes, in fact, this is the causal case. Let's try another example that isn't quite so easy to look up in the table. Very similar, same denominator. H of z, though, this time is 5z to the minus 2 over z minus 0.1 quantity squared. And we still want to find what's the unit sample response, which is the inverse z transform. This time we can go looking in the table to see if we can find a match. And again, the best match we have is the one we found before, but the numerator is off. And so we look in the properties to see if there's some property, some manipulation on the signal that would result in some additional power of z in the numerator, either added or subtracted. And we notice that that is the shifting property. That if we shift by n, capital N, then we multiply our z transform by z to the minus n. And so we could recognize that our transfer function has a time shift in it. The best match we have for it is the alpha z over z minus alpha quantity squared one, where alpha is 0.1. And again, we'd have to scale it by 50 to correct the amplitude of the numerator constant. To get to the z to the minus 2 in the numerator, with that assumption, I would have to multiply by a z to the minus 3, which implies a time shift by 3 samples. So I'll do the inverse transform of our assumed function here with it scaled, and then apply the time shift property after that. So the first part transforms to the same thing it did before, n times 0.1 to the n u of n, and the z to the minus 3 implies a time shift, which means everywhere there's an n, I have to put n minus 3 in, both for the n out in front, the exponent on the 0.1 to the n, and the starting point u of n minus 3. So that's a combination of tables, the properties table and the transform table, for getting us the answer. If I have a h of z or a y of z that's not a complex ratio, not a rational fraction of z polynomials, but a simple polynomial, that usually indicates that it's a finite sequence or an FIR, filter unit sample response. And these we can simply z transform directly, recognizing that powers of z represent time shifts, and individual coefficients, the inverse z transform of a 1 is a delta sub n. And so this first term, if we inverse transform just term by term by term, we have a 1/2 z squared. Well, 1/2 would inverse transform to a delta sub 1/2 delta sub n, and the z to the plus 2 makes that a time shift to delta sub n plus 3. Excuse me, plus 2. The minus 5z, likewise, the minus 5 transforms over to minus 5 delta sub n, and the z to the first power makes it a delta of n plus 1. 1 transforms to delta sub n, and 5z to the minus 1 is a minus 5 delta sub n minus 1 for the time shift, and 1/2 z to the minus 2 transforms as 1/2 delta of n minus 2. So if we have a sequence like this, then it's very straightforward to just term by term inverse z transform it. And we get a bunch of basically sample values. Now, if this was in fact the unit sample response for our system, we would notice that it's not a causal system, because we have h of n is not 0 for n less than 0, if this is my n equals 0 underlying term here. It is a stable system, because again, all finite impulse response systems are stable because their unit sample response is totally, absolutely summable. This particular unit sample response happens to be the response for a linear phase FIR filter. The way I can tell is, again, around the center position of H of n, we have an even symmetry. If I have either even symmetry or odd symmetry around the center point of my H of n, it's a linear phase filter. All right, so then we get into slightly more complicated transfer functions or y of z's that we want to inverse transform, and particularly as soon as our denominator gets above a second order system, when we get to quadratic or to a third order, fourth order powers of z in the denominator, then we're kind of stuck with doing something more than just looking things up in the table. We're going to have to do some factoring. We're going to have to do some partial fractions because there's nothing like this. Again, we only go up to second order in our lookup tables. So if what we're after is nothing more than sample values of the inverse transform, then simple long division will actually get those for us. I can literally divide z squared minus z by z cubed minus 1.5 z squared plus z minus a quarter, and turn the resulting quotient into an inverse z transform that gives me sample values of the h of n, the inverse transform of h of z. Let's see how that works. So we'll set up the numerator, z squared minus z. We'll divide it by the denominator, and z cubed goes into z squared by multiplying it by z to the minus 1. So we multiply the whole divisor by z to the minus 1 and get z squared minus 1.5 z plus 1 or minus 1 quarter z to the minus 1. Subtract those off. We're left with a remainder of 0.5 z minus 1 plus a quarter z to the minus 1. Go through the division again. Z cubed goes into 1/2 z by multiplying it by 1/2 z to the minus 2. So we take 1/2 z to the minus 2, multiply it by our divisor, get this term, subtract them, we get the next term, and we could keep doing this forever, and we would have to keep doing this forever. This happens to be the transfer function for an infinite impulse response system. So its inverse transform, which is a unit sample response, is infinitely long. But every component that I get in this quotient is something that I can inverse transform to a sample value in the resulting inverse z transform. Z to the minus 1 transforms to 1 times delta sub n minus 1. 1/2 z to the minus 2 is a 1/2 delta of n minus 2. Minus a quarter z to the minus 3 is a minus 1 quarter delta of n minus 3, and so on. This one doesn't have a delta sub n term, so a 0 at n equals 0. And that would give us sample values, not a closed form solution, but sample values of the inverse transform. Now, that's may or may not be helpful. Usually that's not terribly useful. Normally we want a closed form analytical expression for what the inverse transform is, something that we can evaluate at any value of n to get the actual value. But if you need just a few sample values, this will work. It's rather like the way we can use, in a time domain, we can use a recursion table to find a unit sample response for an IIR filter, but it's infinitely long. We would have to keep doing it forever to get all the sample values. If we want a closed form analytical solution, our only really option is partial fraction expansion. And the good news is that with one small exception, the method of partial fraction expansion is almost identical for Z transform as it was for Laplace. So going into this, other than learning the special exception that we have to work with for discrete time systems, if you have your own favorite way of doing partial fractions and it works for you, and it works for you in the examples on homework, then by all means keep doing it the way you're comfortable with. I'll show you my way of doing it, which is a generic way that works for pretty much any system, but you're not required to do it my way. The objective of this, though, is to turn our complicated h of z or y of z into something that looks like one of these forms over here on the left, one of these partial fraction terms, which again tend to be first order or second order terms at best. So we want to match up something and factor things into forms that look like that, so that again we can simply look up the results as we did with the other transform lookup tables. Now, if you're not comfortable with partial fractions, well, we get another chance to get good at it here. The idea is, again, we're going to take what is usually a more complicated polynomial ratio of polynomials in z in the numerator and polynomials of z in the denominator, and match them up with these partial fraction terms. Now, if you'll notice, all of these partial fraction expansion terms all have a z in the numerator. Unfortunately, partial fraction expansion tends to break things up with just a coefficient in the numerator and a pole term, a denominator term. And so these are naturally missing that extra z in the numerator that we typically need for the inverse Z transform, the known form of inverse Z transforms of discrete time signals and systems. And so this is the special accommodation we need to make for discrete time systems. We need to get those Z's back somehow. So how do we do that? Well, recognizing that we absolutely need those somehow anyway, need that Z in the numerator, what we're going to do is remove a Z from the thing we're inverse transforming before we start. So if I want to partial fraction expand a transfer function h of z, what I'll actually expand is something we'll call h prime of z, which is h of z divided by z. So it's basically like taking a z out of the numerator and putting it behind your back while you do the partial fraction expansion, and then put it back in at the end. The other thing we have to bear in mind, and this was true in partial fractions for Laplace transforms as well, the thing that we're going to partial fraction expand has to be a strictly proper rational fraction anyway before we even start, meaning the order of the polynomial in the numerator has to be lower than the order of the polynomial in the denominator. So if I have a z cubed in the numerator and a z squared is the highest order denominator, I cannot partial fraction expand that. I can't even do it if they're the same, which is the more common case. However, this extra step of removing a z out of the numerator knocks the order of the numerator polynomial down by 1. And so that actually helps make sure that we have a strictly proper rational fraction of what we're going to inverse, what we're going to partial fraction expand. And so it's actually a benefit. It helps us with that particular requirement. Again, once we do the partial fraction expansion of the version of our function divided by z, we'll get back to our original function by multiplying the partial fractions all by z and have all forms that match up with the table. So the basic method, take whatever it is you're going to inverse transform by partial fractions, take a z out of the numerator and put it away. Then we can write down the partial fraction terms based on factoring the denominator of the function we want to transform to find all of its poles. Give each pole an individual partial fraction term with an unknown coefficient in the numerator. Then it's just a job of finding those unknown coefficients, and we can do that by the same kind of expression we had with Laplace transforms as well. We'll take the function we're trying to inverse transform or that we're trying to partial fraction expand, for each coefficient, we'll multiply that function by the denominator pole term that goes with that coefficient. Take that, that'll cancel one of the denominator factors, take what remains, and replace z everywhere in that with the value of z that makes that pole go to 0, in this case P1. And this is actually how we find residues at each of these pole positions, which is the way we solve that complex contour integral that is in the inverse Z transform definition. Now, we don't have to understand the details of that. We could actually understand how this works algebraically. If we actually take this assumed expansion of our original function and do these operations to it, we can see algebraically how we're isolating each of the unknown coefficients. Like if I want to find K1, I take this whole function and this side and do these operations to it. When I do that to the right-hand side, well, I multiply my first term by z minus P1. That cancels those two out and leaves behind just K1, the thing I'm trying to solve for. All these other terms will have z minus P1 in their numerator and different things in their denominator, so that when I do this substitution, z equals P1, all of their numerators are going to go to 0. So I'll be left with nothing but the coefficient I'm trying to solve for. So algebraically, this little substitution makes sense. Now, there are special cases, a couple of exceptions to the rules where we have to modify the way we approach this a little bit. And the most common one we're going to run into are when we have complex roots in the thing we're trying to inverse transform. Now, if you recall, the design rules that we came up with last time said if I have a pole or a 0 in my system that's complex or imaginary, it has to also appear with its complex conjugate, so that when they combine together to create the coefficients of the difference equation and the transfer function, that's how we get real valued coefficients for the difference equation. We have to have those cancellations of the imaginary parts that come from combining complex conjugates. And so typically if we have a complex pole, its conjugate will be there as well. When we do the partial fraction expansion, we give each of those individual poles their own partial fraction term. Here's one with one complex pole, and here's the conjugate of it. You can notice it's the conjugate because the J part is the opposite sign, but the real part's the same. As it turns out, if we do the partial fraction expansion on these two terms separately, it will always turn out that the coefficients we come up with for their numerators will also have to be complex conjugates of each other. So I don't have to do that. I don't have to do it twice. I can solve for one of these and know what the other is going to be, simply the complex conjugate. So that's kind of nice. I get a 2-for-1 on that. And if we look up in the table, what kind of terms generate these complex conjugate poles? Usually it's sines and cosines will give us them, as will sines and cosines that have exponential weights in front of them. So here's the generic form. Here we have a complex conjugate set of roots, either written in polar form with the denominator and the numerator written in polar form as well, or if the coefficients are written in rectangular form. They both are basically the same basic function. It's a cosine with a phase shift, or cosine added to a sine of the same frequency to produce a phase shifted cosine with some magnitude, some alpha to the n exponential decay, and a coefficient out in front. So rather than just talking through the process, let's take an example problem through one that has a complex conjugate set of roots. And let's say we're doing a system analysis problem, a zero-state response problem. And our system is given to us, described not by an H of Z, but by a pole zero diagram. And here it is. I have a 0 at z equals 1. I have two poles at minus 1/2 plus or minus j 1/2. And into that system, I want to input a 1/2 to the nu of n, a causal input signal. The system starts off relaxed. And in order to find my h of z and completely, I need to know the poles and zeros, but I also need to know a gain, something that's going to tell me about the gain of the system. And that's what this comment is for. It says the frequency response of this system at a frequency, digital frequency 1/2 cycles per sample, has a magnitude of 0.8. I can use that to solve for any unknown coefficients out in front. But let's do that. How do we get our h of z from the pole zero diagram? Well, first we set up the h of z. We have 1, 0 at z equals plus 1. So we have a z minus 1, 0 term in the numerator. I have poles at minus 5, or at plus 0.5, plus or minus j 0.5. So that gives me pole terms at z minus 0.5 plus j 0.5 and z minus 0.5 minus j 0.5. And I also have an unknown gain out in front. Now, we're all set with the poles and zeros. We just do need to solve for that k value, and that's what that little extra piece of information was given to us for. It said at frequency 1/2, this h of z at whatever z represents f equals 1/2 should have a magnitude of 0.8. All right. Well, how we relate h of z to h of f was Wednesday's challenge. And we said the way we do that is we can replace z with e to the plus j 2 pi f and get an expression that's the same as the frequency response or the discrete time Fourier transform. If we start with the transfer function, we get the frequency response. So at a frequency f is 1/2, we plug 1/2 in for f in e to the j 2 pi f, and we see if I want to find the frequency response at that frequency, it's like finding the transfer function at e to the j pi, which is, okay, e to the j pi over here at minus 1. So we can have equivalently evaluate h of z at z equals minus 1 to find h of f at f equals 1/2. So let's do that. H of z at z equals minus 1, according to this, is equal to 0.8, its magnitude. And that would be the magnitude of this expression, where we replace z everywhere with minus 1. Simplifying and solving for k, turns out k is just 1 in this case. And so here's our poles and zeros. Here's our rubber sheet representation. And then the frequency response. We see the frequency response as we start out the 0 here at DC. Rubber sheets pulled down to 0. So the frequency response is 0 at that point. As we come around on the unit circle towards this pole, as we get near the pole, we get some peaking because the rubber sheet's getting pulled up nearby. We ride up the roller coaster here. And then when we get past the pole, well, then we start coming down. And so sort of have a bandpass sort of filter, although without a 0 over here, that tail of the bandpass doesn't quite get back to 0. So I don't know, we want to call this a bat ear filter maybe. So here's our transfer function that we derive from that. It's z minus 1 over z squared minus z plus 0.5 if I combine my two complex conjugate terms. That's our h of z. We want to know what's the output of this system if I put in 1/2 to the nu of n. That's our input signal. So we need its z transform. That's one we can look up in the lookup table. It's z over z minus 1/2. So then we can simply do the convolution by multiplying x of z times h of z to get the z transform of the output y of z. And if we put those all together, we get a numerator that's z times z minus 1 divided by a denominator z minus 1/2 times our complex conjugate pair of poles. That we have no choice but to partial fraction expand. And before we do that, we're going to pull one of those z's aside. So we won't partial fraction expand y of z, but we'll expand y prime of z, where that prime is not a derivative. It's implying a different flavor of y of z, where we've taken out a z. So we'll remove that one from the numerator. So the function we're actually going to partial fraction expand is this one, where I just have z minus 1 in the numerator. I have a third order power of z in the denominator, first order in the numerator, definitely a strictly proper rational function, so I can proceed with partial fraction expansion. We break it up into individual terms with each of the poles. An unknown a with the z minus 0.5 term, an unknown b with the first complex pole, and the second complex pole gets b again, its complex conjugate. So I only have to solve for 2 coefficients, not 3. A we do in the normal manner. Take our whole thing we're trying to inverse transform, multiply it by the pole term that goes with it, which cancels out one of them. Take what's left over, replace z everywhere with 0.5, and the algebra brings us to minus 2 for that value. B we actually solve for the exact same way. Take all of our y prime of z, multiply it by the z minus 1/2 plus j 1/2 term, which cancels one of the ones in the denominator, but not both. Then into what remains, everywhere there's a z, I'll replace it with z equals 0.5 plus j 0.5, because this is minus 0.5 minus j 0.5. And when we do that, we will get some complex values floating around, which we can simplify and express either in rectangular form or polar form. This is either 1 minus j in rectangular form, or the magnitude of that is the square root of 2. The phase angle of that is minus pi over 4, so square root of 2 e to the minus j pi over 4. That's going to be the partial fraction term that goes with this pole. The one that goes with the conjugate then is 1 plus j. We invert the j, the imaginary parts, and we invert the phase angle. So 1 plus j, or square root of 2 e to the plus j pi over 4. So now we have a complete partial fraction expansion. We've solved for a, we've solved for b, we've got b prime. To recreate y of z, we multiply all those partial fraction terms by a z again. And we can either treat them in polar form here, or rectangular form, depending on which one we want to look up in the lookup table. The first term we recognize as a simple exponential term in the table. The second term, if we use the polar form of the coefficients in the numerator, it looks like the entry number 5 here. All we have to do then is pick out what is k, what is phi, what is alpha, what is omega. Now we want to be really careful about, because we have conjugates here, that we match things up with the proper signs. So I'm going to match up here. This first term in the partial fraction has a z minus an exponential with a positive exponent. So that kind of matches up with this one, this term. So I'm going to call 1 over square root of 2 as my alpha. I'm going to call plus pi over 4 as my omega. I'll make square root of 2 my k, and minus pi over 4 as my phi. Now, if I wasn't careful, if I had grabbed this term inadvertently, I could have had opposite signs on my angles. And so got to be careful that you match up the terms appropriately. But once I make those equations, make those determinations of which factor, which coefficient is what in my partial fraction expansion, then we can simply write the inverse transform using the table. In this case, the minus 2z over z minus 0.5 goes to a minus 2 times 1/2 to the n u of n. Equating the k and the alpha and the omega and the phi in this form, we see we get 2 times k, which is square root of 2, alpha, 1 over square root of 2 raised to the n power, cosine n times omega, pi over 4, plus phi, the phase, minus pi over 4, all times u of n. We also recognize that we put in a 1/2 to the n u of n input signal. We got this form of that same signal coming out, so that must be, or most likely, the forced response of the system. What remains is the natural response to the system. So the system naturally responds with that complex conjugate set of poles, the exponentially weighted cosine signal. So we've seen how to do a real root. We've seen how to do a complex conjugate set of roots. The other exception to the rule is what happens if we have a repeated root, meaning we have a multiple pole in our system. Usually that implies we have some n times the inverse transform happening. That can come from a number of different sources. When it happens, like here I have a squared term, pole term in the denominator. When that happens, we need an individual term in the partial fraction expansion for every power of that pole down to the first order. So if I have a second order pole, I need a squared and a first order partial fraction term. If this was a cubed, I would have 3 of them. I'd have a z to the minus p cubed, a z to the minus p squared, and a z to the minus p to the first power. So we include all the powers individually, so there's one term for each power, all the way down to the first order term. The way we find the coefficients, well, for the first one with the highest order term, pole term, we find in the normal manner. We follow the standard procedure, except that we're multiplying our function on this side by the pole term with its highest power. So if we have a squared term here, we'll multiply top and we'll multiply the thing we're inverse transforming by that to the second power, which will totally cancel that squared term in the denominator. We'll evaluate it at that same pole value, and using the algebra again, we can demonstrate how that leaves behind nothing but the A0 term. For the rest of the terms, though, we have to do something more elaborate. And these involve taking derivatives, not of the thing we're trying to inverse transform, thing we called h prime of z or y prime of z, but that multiplied by the pole term at its highest power, that quantity, which is a function of z, we take a derivative with respect to z, and then after the derivative, we make the substitution z equals p2. And again, we can demonstrate algebraically how that leaves behind the next order term, the A1 term in the sequence. If I have more than 2, if I have more than the squared term, then if I have a third order or fourth order or fifth order term, then I need a more elaborate equation. I'm still going to multiply the function I'm partial fraction expanding by the highest order pole term. But I'm now going to take the nth derivative, where n represents how far down below the highest order we're operating at. And I also need to divide that coefficient by n factorial. Now, when might this happen? It happens when you have an h of z, a transfer function that has multiple poles on top of each other. Back in the difference equation days, we would have said that system had 2 roots of the characteristic equation that were multiplicity, that had a multiplicity of 2. They had the same 2 roots, repeated roots. It can also happen when we have that special case where the input signal has the same functional form as one of the natural response terms of the system. In the z domain, that happens when my h of z has a pole at some location, and the x of z Z transform, the input signal, has a pole at that same position. So when I put them together to make Y of Z, I end up with a repeated pole. So here's an example of that. Here's a transfer function in H of Z that's a Z squared over Z squared minus 1, where Z squared minus 1 factors into Z minus 1 and Z plus 1. If I wanted to find the unit step response of that system, I'd be inputting a U of n, which has a transform Z over Z minus 1. The output transform then would be Z times Z squared over Z minus 1 quantity squared plus, or times Z plus 1. And I have a repeated pole. Didn't have that originally in H of Z, but when I multiplied it by X of Z, I got that. Now the partial fractions would be done not on this, but this with Z taken away to make it a Z squared. We'd break this up into a coefficient to go with the Z plus 1 term and two coefficients to go with the repeated pole here, one with the square, one with the first order. K we find in the normal way, which in this case turns out to be a quarter. A0 we find in the normal way, although remember we're going to multiply our function by the Z minus 1 squared to get rid of this whole squared term. Then replace Z with Z equals plus 1, giving us a half. And the A1 term is the tricky one. We're going to take this original function multiplied by Z minus 1 quantity squared. So really it's the same thing that came out of this previous operation. Take that function and take its first derivative with respect to Z and actually multiply by 1 over 1 factorial, which is just 1. Then evaluate that derivative at Z equals 1. That derivative we can work out, taking the derivative of this, treating it like a quotient or a product. Plugging in Z equals 1 into that expression gives us a 3/4. And so we have the partial fraction expansion for our Y of Z. We can use the lookup table to inverse transform. The Z over Z plus 1 goes across as a 0.25 times minus 1 to the n U of n. This squared term comes across as 0.5 from the coefficient out in front. And the Z over Z minus 1 quantity squared is an n U of n. And Z over Z minus 1 is just U of n multiplied by the 3/4, the coefficient. And that's all there is to it. Lastly, if you don't have a strictly proper rational function, it has to be. If we started off with a higher order in the numerator than the denominator, then we'll still have a not strictly proper rational function when we take 1 power of Z away. In that case, if that's what you're left with and you want to do partial fractions, you can always use long division to literally divide the numerator by the denominator, which will give us a whole number value and a remainder, which is equivalently the 1 plus the remainder over the original denominator. So this will give me an equivalent expression to this, so I haven't changed anything. And we'll partial fraction expand this strictly proper part and keep this 1 around, this whole number value around, and inverse transform it separately. You do the division. Oops, back up. We do the partial fractions on this remainder part. Turns out we would find that the coefficients were -2 and 3. Then we would restore the Z to everything, which puts a Z in with our whole number coefficient here, so that it comes in inverse transforms as a delta of n plus 1, Z to the first power, and then the other two terms inverse transform normally. That's the whole story on how we do inverse Z transforms with partial fraction expansion and all the other options that we have. Again, the context of what we would be likely to be using these are finding unit sample responses from H of Z, or as we did the examples here, finding zero state responses by doing convolution, effectively by multiplying Z transforms and then inverse transforming the result to get the output signal in the time domain as a function of n, that would be the most likely case that we would be using for partial fractions. With that, we'll put a dividing line for what you need to be responsible for the next midterm exam. We're going to carry on Monday. We're going to go forward and finally actually get to the place, one of the reasons we came to the Z transform from the DTFT, and that's to lift this restriction of only being able to find zero state responses. Monday, we're going to see how to find complete total responses by using a special version of the Z transform, the one-sided Z transform. So come back for that. In the meantime, finish up homework on this weekend on these problems, practice this inverse Z transform and partial fraction expansion, see if my technique works well for you, or if you want to use one of your own, just make sure you have an operational method that works for you, because I guarantee you're going to need it for midterms and finals. It's an important concept. So please practice up on that, and we'll reconvene on Monday in some new territory. So I'll stop the share here and hang on for any last minute questions that you all have. And if not, have a great weekend. And don't forget to finish up the homework and take a look for that last lecture that I'll be posting later today or tomorrow morning on design of discrete time systems.
Thanks, Professor. Have a
All
good
right.
weekend.
Have a good one. You too.